Okay. So here is a problem, which is an assignment problem. So this says the following. If you have some almost everywhere convergence, then it converges almost uniformly. This is not converges almost every, I mean, this is not, it converges uniformly almost everywhere. It's not that. It is like what is called, it is almost uniformly it converges. See what it means is the following. I have written the statement very, precisely. If you have a sequence of measurable functions, phi n converging to phi almost everywhere, of course, phi is also measurable, you assume that, and assume the measure is finite, then given epsilon greater than 0, there exists a set f epsilon whose measure is measure of f epsilon is less than epsilon, and outside this f epsilon, on f epsilon complement, phi nx converges to phi of x uniformly. That's all. So outside a measure, given any epsilon, given an arbitrary epsilon, outside outside a set of measure less than epsilon, the convergence is uniform. So this is not, it converges, this does not say that it converges uniformly almost everywhere. That means there exists a set of measure 0, outside that it converges uniformly, which is not the case. Here outside a set of measure epsilon, given any epsilon, this can happen. Okay, outside that it is uniform convergence. So to prove that, I have given a hint. You just consider this set, which I have defined. So if you wish, you can copy, or you can, this will be posted in the video where you can look at it again. So you consider this set AKN, where this set where it is phi x minus phi kx is greater than 1 by k. Okay, then you take the union of those sets. Okay, that from I equal to n to infinity, and that gives a set that gives, that depends on n and k. Then you can see that AK, I'm taking the lim inf. AKN, the set decreases to AK, some set AK. Then prove that mu of AK is 0. So that will, because the measure is finite, that will imply mu of this will go to, this will go to 0. So given epsilon, you can choose a nk such that this set is less than epsilon by 2k. Then you define epsilon to be union of such, union over all k. Okay, all ak, nk. It is slightly difficult problem, but not very difficult. Since I have given the hint, it's not very difficult. If you write it, you will get it. So then this mu epsilon this will have less than epsilon because you have already chosen it like that. When you sum it over the 2k, sum it over k, it will be less than epsilon. And here the convergence will be uniform. You have to prove. For all x, that something sum minus, the phi minus phi n, phi nx, phi x minus phi nx will be less than 1 by k. Because that is how we have defined this set. Okay, it's just you have to write it and get convinced. That's all. So I have given the hint. So this is the assignment. Yeah, I hope this is fine. Okay, so if you have copied, it's fine. Do you want to copy? Some time to copy, or you will copy it later?
I've screenshotted the problem.
Say it again.
I took a screenshot of the problem.
You have, okay. You can take the screenshot also. I'm asking others. If anybody wants me to wait, you tell me. Otherwise, I will move on. Okay. Okay, I will move on. So today my plan is to do product measures. Okay.
Sir, by the way, what are the deadline for all the assignments you have given us so far?
So it's next week, next Friday, including this.
Friday. So we can compile all the 5 sets to give
you can do that. Yeah, you can do that. It will be helpful for me. Otherwise, I have to search in my mail and.
Okay.
This is better. Okay. So you can do that. If you don't do, it's not a problem. But I will check it anyway. I will check my mail. So if everything is there, then it's. I think since it's all electronic, you can just submit everything together. Okay. So today we want to do what is called product measure. So we want to construct new measure out of given 2 measures, product measures. Okay. So the reason for doing this, there are many reasons to do that. Because, for example, when you want to take tensor product, define tensor product of Hilbert spaces, this is the way to do it. Then which we may consider later. Or if you want to talk about independent random variable, if you want to say in probability, there is something called independent random variable. So this is one way of doing that. You need product measure for constructing independent random variables. Okay, so that's why we do this product measure. So And we will not be doing probability, independent random variable, but I'm just saying the purpose of one reason for doing these things. So we want to do the following. We have two measure spaces. Okay, mu and y this. So this is a different measure space. So G nu. Okay, these are two measure spaces. Okay. Then we want to construct two things. First, we want to construct a sigma algebra of subsets of x cross y. Okay, you take the direct product and you want to construct the sigma algebra that this is we call it as this tensor G. Okay, this is just this is not cross product. So this is something more than that. So usually people use cross product, but I prefer to use tensor. Some people use tensor. So this is tensor. Because this is so very, this is associated with tensor product in Hilbert spaces. So that's why I'm using this. There is no, okay. So this is F tensor G. We want to construct, this is what is called product sigma algebra. First, we want to construct this product sigma algebra. The product sigma algebra subsets of x plus y and a measure on this. Okay. Okay. So we also assume that we will assume. See, when measures are not sigma finite, there is not much theory. So whatever we do, I will mention that it is sigma finite while writing the theorems. But even if I don't mention, we will always assume mu and sigma are sigma finite. Okay. When it's our sigma finite, there is not much nice theory. It's like having counting measure on real line or something. So which we will not use. Okay, so this is what we want to do. So first we want to construct the sigma algebra. So we are fixing this. Okay, fix this. Let us fix two measure spaces. And then we want to consider this. Throughout this class, we will fix this measure space. Okay, then we want to define an algebra. A is an algebra, which is just disjoint union of A cross B with A in this sigma algebra and B in this sigma algebra. You just take direct product of sets A cross B, then you take disjoint union of such things. Okay. So then the first proposition is it's disappearing. A is an algebra. Okay, it's very easy to verify. Let me see whether I can verify. Otherwise, I will ask you to verify it. Okay, so A is an algebra. So we are taking disjoint union of A. This kind of set, A class B, direct product set. So A is an algebra. Clearly, whole set is there. Of course, clearly this and these are all just you take the product. They are in A. So clearly, this is true. Now,
why are you writing the tensor product symbol instead of the normal product symbol?
This here.
Yeah.
That's because when you consider this is actually tensor product. This is not direct product. When you have x and y, then x cross y is the direct product. Here it is not the direct product of the sigma algebras. Okay, you are not taking two sigma two set here, one set here, and taking the direct product here. What you are having is actually a tensor. What is called is something more than that. So that's why I'm using tensor product. And this is what exactly the tensor product of Hilbert spaces. When you take the L2 of this, which we will define, so like LP, we have L2. So L2 corresponding this mu, which is Hilbert space. L2 corresponding this, which is another Hilbert space. Then when you go through the definition of tensor product, this is precisely the tensor product. The product is the tensor product. That's why I'm using this.
So like if you consider the single algebra given on x cross y given by just by the A set in F times A set in G. So the algebra that you get, is that like coarser or weaker? Like
that's not a sigma algebra, no? If you take direct product, that's not a sigma algebra.
Why?
I'm taking direct product and then taking disjoint union. I'm just claiming now that it's an algebra.
Oh,
And
so this is the algebra generated by those set.
yes, that is a bigger algebra. That sigma algebra is so what I am going to the tensor product is a sigma algebra generated by this. This is an algebra. This disjoint union is an algebra, which I am going to verify now. Okay, it's okay. It's okay.
Yes, sir.
Yeah, okay. So why is this line is there? What did I do? I don't know. I touch somewhere and suddenly something appears. I can't be very careful. Anyway, so I want to verify that this is an algebra. See, what's happening is the following. We have two measure spaces. Then we are taking a set in one sigma algebra and another sigma algebra and taking the direct product like this, A cross B. Okay, this is just the direct product. If you have something like this, you have a set here, you have a set here, then this is this set. Okay, if the set is nice like an interval, the set can be very complicated, then the direct product will also be equally complicated. So you can take something like that, and you are taking all such sets. You take the set, one set in F and one set in script G, then you take the direct product, and that is not a algebra or something. Then you take disjoint union of such things, and I am claiming that that is an algebra. So first thing is the whole set is there, empty set is there. Okay. Then you want to verify that it is closed under finite union and complement. So let us verify complement. It's closed under complements we want to prove. Okay.
Sir,
Yeah. Yes.
How do you define the tensor product for the spaces? Yeah,
Which spaces?
I mean, like it is F
So
tensor
we haven't
G.
defined. I am just going to define. I just
Okay.
said that we want to construct that. I haven't
Okay.
defined it. Okay. I am just defining only thing. The script A is only thing I have defined.
Okay.
Script A is an algebra, which is the disjoint union of this direct product of sets.
Okay.
Okay, we have two sigma algebra. Take one set from the sigma algebra, another set from sigma algebra. Take the direct product, usual direct product. Then take disjoint union. Okay, that is our algebra. That I'm going to prove it's an algebra. Yes. Yeah. Someone.
Sir, yeah, sir, any particular reason for like considering only disjoint unions?
Because we want it to be an algebra, no? There is no other reason. Otherwise, it will be complicated when you take union and other things. I mean, it's very convenient for it. Then you're taking a union. We can see this giant union will look like this. If you take union, it can look like this. Okay, which I don't know whether we haven't considered, but this giant union is something like this. So we want to verify that that's an algebra. We actually want to consider very simple things like direct product like this. But then that will not be an algebra because you can take two disjoint union of that, then that will not be an algebra. So we are taking disjoint union and see whether it is algebra. We want to consider objects as simple as possible so that we can define something on that. Okay. Then there is a sigma algebra generated by that. That is something we don't know, but still we can handle it by proving some existence theorem and other things. So that is what usually happens in measure theory. We still don't know all the sets in Borel sigma algebra, but we know the algebra which generates that. Okay, so it's like that. You can do the character theory extension if you want, but we will do a slightly different way to get this product measure. We will, if you do character theory, then you have to verify other things. We have to verify some sigma finiteness, which will be difficult. But here we will do something else. Okay. So we want to verify it's an algebra. We have defined it disjoint union because it's easy to verify. As you can see that it's easy to verify. So we are taking disjoint union of sets like this. Okay. Now we want to prove that it is closed under complements, taking complements. So if you take two sets, A in this and B in this, then what is this complement? A cross B complement. What is the complement? So as you can easily check here, you can write it something like this. The complement will be much bigger. It will not look like one single direct product, but as you can see, it will look like this. A complement cross B union. This is disjoint union. then A cross B, okay, union A cross B complement. This is disjoint union, okay. This is disjoint, which is clear. These two set disjoint because if XY is there,
how is A cross B in A cross B complement?
how is
A cross B in A cross B complement?
A cross B? What is the question?
I think the second term should be A complement times B complement.
That's right. Correct. Sorry. Yes, you are right. A complement. Correct. So I wanted to write A cross B complement. I wrote A cross B. Sorry. Then I want to write A complement. So this is what I wanted to write, but I wrote this instead. I don't know why I wrote that. I wanted to write this times B complement, so that the this A. What did I write? A times this A complement. Yeah, this is right. This is okay. Then A trace this. Okay, this is okay. Okay. Okay, so this is clear, I believe. Otherwise, you check it. You just have to verify if XY is here. XY is not in this. That means XY is here means X should be in A and Y should be in B. So XY is not here means then one of them should be violated. So one of them is violated means it has to be in this form. Okay, so these are the possibilities. Okay, so this is clear. Now it's clear that this is in, I mean, if A cross B is there, this is in E, right? By definition, this is disjoint union, and this is in K. So similarly, if we have disjoint union of these things, disjoint union, I mean, this is for one such set, one such cross product. But if we take disjoint union of that, then again the same thing will happen. I mean, because it is just what will be that? If you take disjoint union, that will be intersection, no? Okay, so this is for single set, I mean, when the union is single union, I'm proving. Next, I will prove that intersection of such sets is there. Okay, that will follow. Okay, I mean, if I prove that intersection of any two set in A is also again in A, then combined with that will prove. And because if you take disjoint union of these kind of sets, then if we take the complement, it will become intersection. Okay. So you have proved that for a single set, single such union, I mean, when there is only one set in that union, this is true. Okay. Now I want to prove that next claim is, so this doesn't prove that it's closed under complement. We have to do something more. So now the claim is A is closed under intersections. Okay. Okay. So once we prove this, then combined with this, it will prove that A cross B, I mean, this is A is closed under complements. Okay. So the claim will combined with that will imply A is closed under complements. Okay. Okay. So now we verify that the proof of the claim. Now we verify that A is closed under intersection. So what does it mean? We have to, but that is just clear. If we have A cross B intersection C cross D, okay. So, I mean, we need to take finite union. Let's directly take finite union. So union of AI cross BI, okay. Intersection union of, so I varies finite I equal to maybe 1 to n, j equal to 1 to m, cj cross dj, okay. Then this is just union of I equal to 1 to n, j equal to 1 to m, okay. Ij between 1 to m. So each individual thing, okay. Okay, this is just clear. Now it is just AI intersection Cj, then I mean, this is just right. Tj. So this is in A. Okay, this is clear. Now, because of this, combined with that, we have proved that it's closed under complements. But then we have used, we have already proved that it's closed under finite, but this is just one intersection. But then by induction, closed under finite intersection. We have already proved it's closed under complements. So this implies it's closed under, I mean, it's closed under finite union also. Closed under complement and finite union. Okay. So it's proved. Okay. We have proved that it's an algebra. It's closed under complement. It's closed under finite union. So it's an algebra. Okay. So now we define F tensor G to be the sigma algebra generated by A. Okay. So this is the sigma algebra generated by A. Okay. So now what do you want to do? So now we want to define a measure on this. So this is a sigma algebra. I mean, this is a sigma algebra. This is a sigma algebra generated by this. Now we want to prove the following theorem. So before this proposition, I want to make more definition. We want to consider what is called sections. Okay. So this is a sigma algebra generated by this. For this, we want to define the sections. So if for E in this set, okay, you have a set in the sigma algebra, define EX. Usually someone will be there in the video. I don't see anyone. I'm talking to myself. Okay. So for E there and X in X, okay, define EX to be all those Y in Y such that XY is in E. Okay. Similarly, for Y in Y, define, maybe that will be the usual notation, put the X down. Okay. EY, I'm putting on top to make it, I mean, this is something different from that. EY equal to all those X in X. So this is contained in Y, of course, right? Contained in Y, such that XY is in E. Okay. This is, of course, contained in X. Okay. So EX is contained in Y, EY is contained in X. So given any, if you can just fix a X in X, capital X, and small y in capital Y and define the sections. These are what is called sections. Okay, then we have the following proposition. Okay, so we assume we have those sigma algebras and E like this. I mean, I don't want to write all those things. We have two sigma algebras, we have two measure spaces, and we have constructed the product sigma algebra. Then the following statements are true. One is, so we have assumed E is in the sigma algebra, okay, in the product sigma algebra. Then EX is in the sigma algebra, and these are the claim. So EY is on the top. EY. So this is EX is contained in Y, so it is in G, and this is contained in X, so it is in script F. Okay. So this is true. Then the second one. What happened? Suddenly there was a flash. The screen is there. Okay. So then this function X going to, so EX is in G, okay, and it's a second sigma algebra where the measure nu is defined. So nu of EX, okay, is measurable. This is a function. Okay, this is a function. Okay, is measurable. This is a function which takes values in this. Okay, this is a function from X to this. Okay. it may take the value infinity. It's a function, x going to nu x is a function which is measurable. It's a measurable function. Similarly, y going to mu of e y, y on the top, where this is a function from y going to 0 infinity, is also measurable. Okay. Okay. So these are the two things. And these are all measurable with respect to the corresponding sigma algebra. Okay, it's understood which sigma algebras are there. Okay, further integral. So now we have a measurable function. Nu ax is a measurable function in x. Okay, it's a function. I mean, it's a function from x. So you can integrate with respect. You can think about integrating with respect. It's a positive function. So any positive function, positive measurable function can be integrated. So we integrate this with respect to d mu, which is exactly equal to this function y of this mu of e y, okay, d, one second, yeah, d mu, it's right, okay, it's clear, I have written it correctly, okay. This is, you are fixing the set E, then you are defining the sections like that, and using those, and the first thing verify is that those sections are measurable sets. Okay, you have a measurable set. You have constructed a sigma algebra. Okay, we started with two sets x and y. From that we construct the product space. In the product space, the product space is just a direct product x cross y, and in the product space we constructed a sigma algebra, which we called as tensor product of sigma algebra. And when you have any set in the tensor product of sigma algebra, then we take it's not a projection, we consider the section. When you fix a x, we get a section, Ex, and correspondingly we get an Ey. And first statement is those two sets are measurable sets. And then the second statement is when you apply the function, the measure mu on that, that's a measurable function. So the x going to nu ux is corresponding measures. Then that's a measurable function. Then you try to integrate those functions. When you integrate it, you get the same value. So this is the statement of the proposition. Okay. Now we want to prove this. Okay. So the idea of the proof is, I mean, even though it looks complicated, there is no magic involved. The idea of the proof is as usual. We will verify for the sets in those algebra. We have an algebra. We'll verify for that. Then it's a usual idea. I mean, which we have already applied. Then we consider all the sets which satisfies these things, these properties. And we prove that that's a sigma algebra. So everything, it will be satisfied by every set. Okay, this is a standard thing which we have been doing. This standard trick which we have been doing. So, but we have taken algebra, so we will use the monotone class lemma also. Okay, we will use the monotone class theorem or monotone class lemma, whatever which we will use. So first we want to verify.
Yeah, so the statement of this, it's like sort of changing the integral in R2. I mean, similar to that sort of thing.
This one, the last one, yes, that's what we are basically doing.
Okay.
We are going to prove what is called Fubini's theorem, which is like, I mean, the double integral is defined through something else. Double integral is an iterated integral, right?
Yeah.
That is the statement in double integral. So that's what we are proving now. I mean, this is just a lemma or something. I mean, something before the theorem. We are going to prove a theorem called Fubini's theorem, which is just double integral is just the iterated integral. You can write it as two. You can compose two integration. I mean, one integration, you can perform another integration. So that's what we are doing. Okay. Right?
Thank you.
Okay. So we want to prove this. So how do we prove? We want to verify it. First we verify for sets in that algebra A. So that's what we want to verify. So how is any set, any algebra will look like? Let E equal to some disjoint union of some n. So AI cross BI with AI in this and BI in this. Okay. So you have been using those double integrals in your, earlier calculus, multivariable calculus. So we are just proving the measure theoretic version. Yeah, that's all. Okay, so this is our E. Okay, then what is Ex? So we want to verify the theorem, all the statements in the theorem, statement 1 and 2 of the theorem for this. Then what is Ex? It is clear what is Ex. Ex equal to so Bi if X is in AI. Okay, right? Right? Yeah. So, and equal to empty set if X is not in any of those AIs. Empty set if X is not in AI for all I, right? Correct? Similarly, EY equal to AI if X is in BI equal to empty set if X is not in BI for all I. Okay, so clearly these are a measurable set. I mean, depending upon where X is fixed, okay? Given any fixed X, arbitrary but fixed X, we want to prove, verify the measurability. So X, if X is there, X will be in one among this choice, or Y will be in Y will satisfy one among these choices. So EX and EY are measurable. Clearly, EY is measurable. Okay, that's done. Okay. So next we want to verify this set. What is mu? We want to verify nu of that. Oh, what did I do? Okay. Okay. So now we want to consider this set. What is nu of EX? EX is a set in Y. So what is nu of EX? So from this definition, it is clear what is nu of EX. So it is going to be AI if X is in BI. So we can write it like this. Nu of this, I mean EX, we want this BI, nu of BI times the indicator function AI, right? Mu of EY equal to summation mu of AI indicator function BI. It's clear. Just the definition. What we have verified earlier, this is the definition of EX and EY, which is written here. Okay, if you just write it, it will become like this. That is clear. So these are all simple functions, so clearly measurable. Okay, hence measurable. Okay, so the first statement is verified. Okay, second statement is also verified. Then this moreover statement, whatever moreover, the further statement that has to be verified. That says integral of one of the function with d mu is same as the integral. That's clear. Now integral of nu of Ex d mu over X. You will have to integrate. This is a simple function integration, which is just summation over I nu bi mu ai. Okay, and integral over y of mu of ey d nu is also it be. I mean, this is just a simple. I mean, these are all numbers. This mu and nu, they are all numbers. Okay, and it's also same thing. Okay. Mu of ai mu. Okay, these are two are equal. Yes. So these two are equal. So it's verified. The proposition is, this implies the proposition is verified for E in A. We have verified for the sets E in the algebra A. Okay. Now we want to prove the theorem. To prove it, we only have to verify. Let I need a notation. Let this be the collection of all sets all E in this. See, E satisfies the proposition. All the condition in the proposition. So it is enough to prove E is a sigma algebra. Okay. And it's enough to verify. Enough to verify E is a monotone class. Okay. It's closed under increasing union and decreasing thing. But the first thing, two statements we don't need increasing union or decreasing thing. They are, I think, direct. What is the first statement? The first statement is EX is, but then if you have, so first statement is if EN is a collection contained in this, okay, then, so we want to verify that it's a sigma algebra. So first, okay, let's come to complements after this. Then we want to talk, so, I mean, it's an E we want to have. We want to have this is in that E. Then we want to prove that it is closed under disjoint union, not disjoint union, countable union. Okay. Then union En. If En is, that is, it satisfies other properties also, but let us assume this property. Enx, Eny is in this, and this is in G. Okay. Then union of Enx, this is just direct verification. I don't have to do much. Equal to union Enx. Okay. So union En is in this. This is just verify. You just, by the definition, it follows just from the definition. If you have X, then XY has to be in the union. So it has to be in one, Y has to be in one of them. And it is same as that XY has to be, Y has to be in Enx. Okay, it's clear. This is clear. Similarly, E complement X equal to Ex complement. Okay. So okay. So we only have to verify the other properties. What are the other properties? The measurability properties and the integral property. For that, let us assume increasing union, because we know that we want to take limits. Okay, so it will be nice. Suppose we want to prove that the script E, which we have defined here, is a monotone class. That's what we want to prove. Okay. So suppose En is contained in this E, and En increases to E, and some Fn contained in E, and Fn decreases to F. Okay. Then we want to verify that E and F are in E. Then we are done. That's what we want to prove. Okay. So for the time being, first step, assume, because we want to apply the convergence theorem which we have proved. For increasing does not matter, but decreasing we need this assumption mu and nu are finite. Then we will take increasing union of set, and we will prove for sigma finite sets. Okay. So first assume that these are finite. Okay. Okay. Then what happens? En increases to E, so Enx right, and Fnx decreases to Fx. These are all clear. The same thing which we have verified earlier. The same thing which is true here. So these things will imply that since we have assumed the measure should be finite, these things will imply that mu of Enx will increase to mu Oh, sorry, this should be new, no? This should be new. I'm sorry. Okay. New of EX and I mean, we have to verify for the Y also, but it will be the same verification. So we will not do that. Okay. So we are just only doing for the X and new of E, sorry, F. Fn X decreases to new of Fn Fx. Okay. So I am seeing only one person who is also not a student. So if somebody comes in the video, it will be better for me. Otherwise, I'm talking to myself, as I told you several times. Okay. Fx. Okay. So then we have already proved limit of measurable function is measurable. So this implies x going to nu of Ex. Okay, x going to nu of Fx are measurable. Since we have already proved that limits of measurable function is measurable, and because of that, this is true. Okay. Okay, so this is done. So the measurability part is over. Now we have to verify for the integral part. But then it is not that so because now this is increasing, the first statement is nu Enx. This is not B, this is nu Enx, Enx increases to nu of Ex. Okay, as functions. Okay, for each x this happens, for all x. Okay, as functions. I mean, this is x going to this function. So by MCT, which you have proved in the last class, integral nu Enx, sorry, nu En and nu Enx, right? D mu over x. Okay, this also increased to integral over x nu Ex d mu. Okay. Okay. Similarly, the other one. So no, the other one you need Lebesgue dominated convergence theorem. Now you see that nu of Fnx. Okay, this is a function x going to this. This is a positive function. Of course, the positive value is less than nu of. So this is in x. Sorry, this is in y. Nu of y, which is less than infinity. We have assumed that the measures are finite here. So this is less than infinity. And this is a constant function. Okay, this nu y is a constant function. This is for all x. This is true for all x. Okay, and integral nu of y du mu. Okay, over this is a constant function. Okay, nu of y, which is over x, which is equal to nu of. It's happening. Yeah. This is equal to mu of x, nu of y, which is less than infinity. So this constant function is integrable. Okay. So our Lebesgue dominated convergence theorem says that if you have a sequence of function which converges to some other function, okay, everything measurable, and if all these functions, all those functions in the sequence are dominated by one integrable function, okay, I mean the mod, I mean it's dominated by the integrable function, then you can take the limit inside. So here we have these functions. Okay, for increasing we don't need because these are all positive functions. For increasing we just used monotone convergence theorem, MCT. For the decreasing limit, we need dominated convergence theorem. So all this, the mu of this is dominated by this constant function, which is integrable because it's a finite measure. It is integrable. Okay. So because of this, by LDCT, Lebesgue dominated convergence theorem, we have that integral of nu of Fn x, okay, d mu over x converges. Okay, this is just a conversion over x nu of Fx d mu. Okay. Right? So these things imply, what does this imply? X going to nu of ex, x going to nu of, sorry, this is mu, and this is okay, mu x going to fx are measurable functions. Okay, that's what we have done, right? So these are measurable functions which we can again integrate, and as now what do you want to prove now? Let me get, and shouldn't get convinced. So what do you want to prove? We want to verify this integral, okay? But then we have, we have already verified all those things. We have that integral of nu en x. This is the assumption. We are assuming, we are taking those sets en and those set fn in the script e, which is which we want to prove it as a sigma algebra, which is a monotone class. That's what we want to prove, which is closed under increasing union and decreasing intersection. That's what we want to prove. And we have also, they are in E, so they satisfy this condition. This is equal to similarly, I have only verified for E and X. Please verify, in the same way we can verify it for the, I'm not writing it, okay? Similarly, the other condition is also satisfied. Maybe we can call it something. This condition, the other condition. So we have verified the first condition, this condition. So this condition is also verified. Maybe you call this star 1, this is star 2. So here we have only verified star 1. Okay, so this implies star 1 is verified. So similarly, star 2. Okay, star 2 can be verified. So now I am take since they are all these ens are in sets in the script E. So this satisfies this mu of fn. Sorry, en y d nu, right? It satisfies this. Similarly, this x. This is f. Okay, fn y d. Sorry, this should be mu d nu. So it satisfies this equation. Oh, is okay. This is okay. So this is satisfied for all n. Okay. Now we know that. So then the limit will also satisfy those things. Okay. It's okay. You can replace this en. Say here also it's en. Okay. Okay. So maybe I will call that as dagger, this equation. Okay. I don't want to write the whole thing again. This dagger. Then this implies E and F satisfies dagger. Okay. So we have verified that. So this thing verifies that this is a monotone class. Hence, by monotone class lemma, hence a sigma algebra. Okay. Lemma. So now we have to verify. Now we are only left with verifying for the case sigma finiteness. Okay. Now suppose mu and nu. So how much time I have? 51. Sigma finite. Maybe I can ask you to verify. Okay, I will verify it. It's very easy. So what does it mean by they are sigma finite? There exists set xk contained in x and yk contained in y such that mu of xk is finite, nu of yk is also finite, and x equal to union of xk and y equal to union of yk. Okay, k equal to 1 to infinity. It's from countable union. Okay, that's what it means by sigma finite. Then we know this is an increasing union. Then we know that x cross y equal to union of xk cross yk. Okay, right? Is okay. Okay. Then what happens? Then if we have a set E, then we want to, what do you want to do? We want to verify this thing, this finite union and all those things. Okay, so now this, I mean, we are taking this ENs and other things. Okay, suppose EN increases to E, all these things are happening inside F. Okay, and Fn, sorry, F tensor G. Okay, similarly, Fn decreases to F. All these things are happening inside this. Then you want to verify the corresponding convergence. Okay. So what do we do? So we have this En. So we have to take some, we have to restrict the measure. Okay, so take mu k is mu restricted to xk and nu k equal to nu restricted to yk. Okay, that's right. Okay, then this E, let's forget about that. Let's let me just write something and then okay. Now this Ex, okay, Ex intersection yk, we fix a x, okay, for any x and any E, okay, this will increase to in k, okay, this will increase to Ex, right? Similarly, Ey, okay, intersection this xk will again increase to Ey. Okay, so this implies nu k of Ex, which is a function, okay, function in x, of course. So which is equal to, which we have defined, which is just the restriction. By definition, this is mu of Ex intersection yk. Okay, so this will increase to mu of Ex. Okay, sorry, this is mu. I'm sorry. This is new. So this sorry, this should be. This is okay. New. Is it okay? Anybody listening?
Yes, sir, we're all listening.
You are listening, so you are following also. Okay, this thing you can verify directly. So okay, so this nu k Ex. So this thing increases. Then you just have to use again monotone convergence theorem, maybe once or maybe twice. Okay, so you have to. So first thing is so we have to use monotone theorem. No, we have to use just monotone theorem, monotone convergence theorem. These are all functions. Okay, these are all functions in X. Okay, so this increases to this. So it will imply that the integral, I mean, so the corresponding measurability will follow because those things increases, and it also follows that nu k Ex. We know that, I mean, we know d mu will be equal to limit k going to infinity integral over, sorry, there is no k here. Okay, nu k of Ex d mu. Okay, and we know that these things are equal to mu k. I mean, we are just very restricting to the, I mean, you have to work with the xk cross yk. For that is true. Okay, I'm not writing all those details, but it is clear. We have by u on xk cross yk, which increases to x cross y. Here you can you can consider the measure mu k cross you can consider the mu k and we haven't defined what is mu k tensor mu k. So you can consider mu k on this and mu k on this. And for that, this is true. Okay, mu k of ex. Okay, t mu. Okay, so now this is equal to integral over mu of e. I'm sorry, this has to be e y. No, this has to be ey. Right? This is new. Okay, mu of ey d. Okay. This is okay. If you have any problem, I will go through this, but I'm quite bored with this. You should be able to verify. Okay. You have already done enough calculation. So this is just, you are using MCT anyway. You are using MCT. This is MCT. Okay. Here also it is MCT. Because of MCT, these two things are equal, but they are equal because of our assumption. Because we have not our assumption, because we have proved it for finite measures. So all these things are equal. So this is true for any sigma finite measure. Anyway, it's an easy verification for a sigma finite measure. Okay. So it's 5:58. So I will prove the next theorem in the next class. Okay. So if you have any doubt, we can discuss, even here or in the assignment or anything. It's okay. Everything fine?
Sir?
Yeah.
Sir,
Yeah.
is there a concept of product of arbitrary measure spaces?
Without sigma finiteness. Is that what you are asking? What
No, I mean, for over an arbitrary collection.
when you can
Let's
do it for
suppose
two, whether you can do it for
I
anything,
in
you are
some
asking.
indexing set I xi.
Yeah, that's possible. Should be possible, no? No, countable thing, it's possible, but arbitrary thing, there will be a problem, no? Arbitrary thing.
So countable, you can like assign a weight of 1 by 2 to the power I for each I and then take that.
No, you will need some more condition. We will come to that. See, for example, it is like tensoring. As I told you, we will define Hilbert space, and it's like tensoring the Hilbert spaces. Okay, you can do countable tensors, infinite tensor you can do, but you need some more. You need some, whatever you can make sense of it, you can just write it. You need some sort of convergence in that. So you need some more conditions. Okay, it is possible to do it for countable infinite tensors. For infinite thing also, you can using some finitely many things you can take and then take the corresponding. It's easy to do it using Hilbert space theory. Once you have defined for finite tensors, then you can define finite tensors and then you can complete it. There's some completion we can do. It's possible to do, but it's not like this. Okay, once we do it for two, say it again.
Can you use transfinite induction for the assignment problems?
Which assignment problem?
Transfinite induction.
For what?
For example, in general, many of the theorems of major theory are much easier if you use transfinite induction and show that the sigma algebra generated by a set is
possible. Yes. So
can you use them in the assignment problems or the exam problems? Is transfinite induction?
Oh, you can use, that is a mathematical theorem which we assume always. We assume maximum of choice and all those things. But where is it? Where do you encounter that? I don't see anywhere.
No, for example, this just to listen. For example, just open the notes.
You have something in the assignment. I don't see where you have to use transfinite induction.
You don't notice, but many theorems are. So, for example, this thing, to show that the supremum of this thing is equal to this, that mu of random measure problem. It's online if you use transfinite induction.
Supremum of what?
Radon is in the radon measure problem.
Okay. There. Okay. Yeah. You can assume anything. I have asked you to assume very simple things and write that, but you can do whatever.
We can assume axiom choice, right?
Sure. Axiom of choice is assume. If there is no axiom, that's not mathematics as usually. We always assume axiom of choice in mathematics. Okay,
Okay, isn't transfinite induction based on axiom of choice?
say it again. What is it?
Isn't transfinite induction based on axiom of choice?
Yeah, you can prove transfinite induction assuming axiom of choice.
But this equivalent, like axiom choice, transfer index, and John's lemma.
Say it again. I'm not hearing
Like
you.
these are equivalent, right? Transfer
Yeah.
index, axiom
Yes,
choice.
one will imply the other. Yes. Yeah. If you assume that, you can prove it's possible to prove that. Right. Okay.
Okay, and can I give an explicit example of a Lebesgue measurable set which is not in the Bode signal algebra of R over R?
Should be. I have to see. I mean, I don't recall immediately. Okay, there should be something.
Okay, so like one way to see that there exists any such thing is that any subset of the Cantor set is measurable using Lebesgue measure.
That's right. No,
But-
yeah, that's one thing. No,
But
you can take any subsets of the Cantor set. We have that is how we have proved it. See, we showed that Borel sigma algebra is not same as Lebesgue sigma algebra using the Cantor set.
yeah,
Because
but
any
so-
subset of a Cantor set, then the power set of the Cantor set is. I mean, we used cardinality. Then you can get some subset of Cantor set which is not measurable. I mean, which is
So-
not in the Borel sigma algebra.
So we know that there exists a subset, but is there only 5 instance subjects which is not in the Bode signal algebra?
I never worked out it. I
Okay.
didn't read such things. Okay. I mean, you can, if you are interested, you can read those things. Okay. I'm more interested in this kind of concrete. I didn't read it. I mean, okay. There should be something. Somebody must have said. You ask B.B. Rao, he will know all those sets in his fingertips. Okay. He will tell you something. Okay.
Okay.
Okay. Okay then.
Sir, next week, can I present Petish measurability theorem?
Next week, he is presenting something, no? So after that, maybe you will think about it. Why don't you write me a mail? I will tell you the precise time. Okay.
Okay, sir. Okay, sir.
Yeah.
And this is kind of a vague question, but what is the intuition that some analog of dominated convergence theorem will fail for Riemann integral, but it is true for Lebesgue integral?
Say it again. Analog of dominated convergence.
Dominated
theorem.
convergence theorem, like what is the intuition that it fails for Riemann integration, but it holds for Lebesgue integrals?
No, dominated convergence theorem. It doesn't fail for Riemann integration.
It does, right?
No. Riemann integration also. But limit may not be Riemann integrable. That's the problem. Oh,
Yeah,
you
yeah,
are okay. What is the intuition? There is no intuition. Riemann integration. I mean, the Riemann integrable function. The collection is not a nice collection. That's all.
Okay.
So that's the thing. I mean, it's on its own, it's not a nice collection. The theory is not nice, a very complete theory, because here you have something which you can have a complete metric space or something. You can have a metric on that. You can define a norm on that, and you can complete and all those things you can do. So Riemann integration is not that nice. That's all. Okay, there is no. So that is why we do this by this. I mean, that's why we need to develop this integration. Okay, shall I close?
Okay, sir.
Okay, goodbye.
Sir?